Okay, this is Mr. A. I'm going to lecture on atomic basics. First of all, I want to go over the relationships that we have for the number of subatomic particles in all the different kinds of atoms of elements that we have. I'm going to review with you the element symbol notation for describing how many of the different particles are in a particular atom. We're going to draw a Bohr model, and we're going to talk about the differences between the chemical symbols and what's in the box on the periodic table. And we will practice one of those big tables where you have to, if you know two things, you can find another. Basically, I'm going to give you all the information that you need to do well on the assessment coming up at the end of the class, as well as give you some practice. So first of all, I want to start off with our basic relationships, how we figure out how many particles are in a particular atom. Now remember that the atomic number equals the number of protons. It's the number of protons that determines what element it is. So if we know that we're dealing, for example, with atomic number 6, we would look in the periodic table, either in the back page of your textbook, or we go up to the periodic table, or we would, I don't know, shout out in the classroom, hey, who has 6 protons in their element? Carbon does. Yes, absolutely. Okay? Now, if you have a pile of carbon, you have a pile of carbon atoms. And you learned in the beginning of the year that an element has all the same atoms, but that's not quite so true, is it? Because there's some differences in the carbon atoms that make up a pile of the element carbon. What are the differences between one carbon atom and another carbon atom? The number of neutrons, right? So the number of so we have different isotopes of carbon. We have different isotopes of carbon because our definition of an isotope is, well, it's atoms of an element that have different numbers of neutrons, right? So we remember that. So today I'm going to pick on carbon-14. Carbon-14, and everybody gets excited about carbon-14 because carbon-14 is the radioactive element of is a radioactive isotope of carbon. We use carbon-14 for carbon dating. We can figure out how old things are way back into, I don't know, maybe as far back as prehistoric time, using carbon dating. Carbon-14 is a real isotope of carbon. What does 14 tell you? It's the mass number. Yes. All right. So if I was to use isotope notation, I would say, I would write it, this is isotope notation for carbon-14. And I got you guys to all repeat, like back in grade school, the dash number is the mass number, right? Let's do it. The dash number is the mass number, right? So let's write that down here. So the dash number is the mass number. So the dash number, the dash number, I'll write this in quotes. I am going to, over here, I'm going to start drawing a Bohr model of the atom. You could, if you're working vertically in your paper, maybe you could put it over here. Over here, because I just want to use the whole board, I'm going to draw and you should do this too, draw a nucleus. And then I'm going to draw some energy levels, this being the first energy level, this being the second. So this is kind of a template for any Bohr model of an atom that I would draw. Mr. Anthony, if I was going to draw a Bohr model of carbon-14 and I wanted to draw protons, where would I locate the protons in my Bohr model? In the nucleus. Okay, so how many protons do I have in carbon? 6. So I'm going to draw 6 positively charged particles in my nucleus. 1, 2, 3, 4, 5, 6. And I'm going to use blue for the other subatomic particle that has mass. What is the other subatomic particle that has mass? Neutrons, right. So protons and neutrons have mass. All of the mass in the atom is located in the nucleus, so my protons and my neutrons have to go in the nucleus. Now, how many neutrons are going to go in the nucleus? Okay, Kaylee, how did you figure that out?
The mass number is 14, and both of them are approximately 1. Both the neutron and the proton are
Yep.
approximately 1.
The basic equation that I gave you, and you can look back and probably find this in your notes, is that the mass number is equal to the number of protons plus the number of neutrons. It is simply a sum of the number of subatomic particles that actually have mass in the atom. And since protons and neutrons are the only particles that have mass, then we add those two up. Now, the question was, how many neutrons did we have? Now note that this equation has 3 variables, and if you know any 2, then you can find the third. Because I'm pretty sure that there are people in this room that can solve this equation for a number of neutrons. You just rewrite it where you are subtracting the number of protons from the mass number. The mass number is always going to be the bigger number, so just subtract whatever the smaller number that you know, and then you get the other one, right? So in this case, exactly right, Kaylee, the number of neutrons is equal to the mass number minus the number of protons. Now you could write that underneath here and have another mathematical relationship, and you could have another mathematical relationship for the number of protons that is simply equal to the mass number minus the number of neutrons. I trust that you guys can manipulate this equation or solve for any of the one you don't know if you know the other 2. But this is important when you go out and filling out that big table. This is an important relationship. Okay, so, here I got my blue marker in my hand, and I'm going to, let's see, number of protons is 6, the mass number is 14, so number of neutrons is 8. Okay, so do the neutrons have any charge? No, so I'm going to write them as just little particles without any charge. 1, 2, 3, 4, 5, 6, 7, 8. I don't know. I'm just going to squeeze them in there, and you can too. Now, because I want to make this an interesting example, I'm going to give this particular atom an overall charge. If you are asked a question about how many electrons a atom is, and they don't tell you anything different, you can assume that the number of electrons is equal to the number of protons. Because protons have a positive charge, and electrons have a negative charge, right? So if I have as many positive particles as I do negative particles, then the sum of those opposite charges they'll negate each other, right? They'll equal to 0, 0 charge. But I want to make today a little bit more interesting. I'm going to switch over to my green pen, and I'm going to write a charge of a +1. This is my element symbol notation. This is my isotope notation. And this is my Bohr model. Where are the electrons located in the atom? In the cloud. I don't know. The camera can't see it over here, but I have a cloud model of an atom, and you can see all the fuzziness kind of looks like a cloud. The electrons are supposed to be these little dingleberries that are kind of out on the end, but there's probably some more up in there. But this is the cloud model. This is the Bohr model. On the Bohr model, where are the electrons located? On these energy levels, these rings, these orbits, if you will. This does kind of look like a solar system, a planetary system. When I talk about these rings, I'm going to refer to them as energy level because it's important to your learning in the next step when I associate Bohr models with the periodic table, these energy levels. Now, yes, they go into energy levels, but I want to ask you, you all had the experience of interacting with the PhET sim build an atom. and you had a bucket of protons, and you had a bucket of neutrons, and you had a bucket of electrons. And you were able to click and drag particles out of the buckets and then place them into the atom. Now, at a certain point, you kind of lost control of where those things go. The sim took over and placed them for you. So if you were grabbing a proton and a neutron, the sim at some point would take over and place those particles in the nucleus. And that made sense because that's where the particles belong. If you tried to place a proton out in the cloud, it would say, and it would drop it back in the bucket. You had to at least get close, right? Do you all remember this kind of behavior that the sim had? So now that you're thinking that way, I want you to think back, what happened to the electrons? When you grabbed your first electron, where did it force you to put it? Not in the nucleus, but in the first ring. It forced you to put the electron in the first ring. So I'm going to go ahead and pretend I'm in the sim, and I'm going to put that first electron here. Electrons have a negative charge. Please indicate a negative charge with a little negative sign. Now then, there's something that you need to know, and you will know, and you'll never be able to forget it in a couple of weeks. And you may or may not have noticed that when you go to load the second electron in, it also goes into the innermost ring. But does anybody remember what happened to the third electron you tried to load? It went to another energy level. And the reason is the first energy level was full. Think about it like this. Like charges repel each other. This inner ring is so small that once you put 2 in, you can't put any more in. It's kind of forced to the outside. So when you build atoms, you build from the inside out. So when you load electrons into a model of an atom, you load them into the innermost ring first, and then you start filling on your way out. Okay, so how many electrons am I going to include in this model?
Are we going by that?
Yes, we're going to build this atom.
So we need 5.
Okay? Tyler, how many? How did you figure that out? Okay, he does this in his head. You don't have to do it in your head if you have this in your notes. Charge, let me write that in green. Let's see if this works. All right, so we have a charge of 1. We have 6 protons. What number subtracted from 6 equals 1? 5. Okay, 5, all right? We know the first 2 go in the inner ring, so for a total of 5, then we know that there must be 3 in the outer ring. Wait a minute. Wait a minute. We've got 1, 2, 3, 4, 5, 6. Okay, 6 positive charges. 1, 2, 3, 4, 5. That means that there's 1 more positive charge and a negative charge. Yeah, we did it right. Okay. Okay? I think we have it all figured out. That is a complete Bohr model atom. What you might want to do right now is label these particles. Electrons with negative charge. Then we have protons with positive charge. And we have neutrons with no charge. You might make yourself some notes, I don't know, based on what we're talking about. First 2 electrons in first energy level. So this tells you a lot. Carbon 14. Carbon tells you 6 protons. 14 is the mass number. From that, you can figure out the number of neutrons. Once you know the number of protons, neutrons, electrons, you can make yourself a Bohr model. Okay, I want to ask you for a moment. Let me make just a little bit of room on my board. This is your element symbol notation. Okay. What is the difference between this element symbol notation and the box on the periodic table for carbon? Let me see if I can get somebody else to pipe in here. Anybody? Anybody? What is the difference between these two? Oh, careful. This is showing a charge. This one doesn't show any charge, so that's the difference. What, Corellia? This is the decimal number is this is the average atomic mass. Good. This is what I wanted to point out. This is the average atomic mass. Not to be confused with the mass number. Okay? In a minute, I'm going to remind you how to fill out these tables, and there's going to be a column for mass number, and I'm going to say, don't put a decimal number in there. This is talking about one particular atom. This is talking about the element which has all the different isotopes. This average atomic mass number is the average mass of all the isotopes. So Brenda, since this is your element, what is the most common? Who's carbon? Who's carbon? Okay, Olivia, what is the most common isotope of carbon? Yes, it is 12, right? You look at the average atomic mass, you round it to the nearest integer, and that's the mass number of the most common isotope. I wasn't talking about the most common isotope of carbon today. I was talking about the radioactive isotope of carbon, which is carbon-14. The most common isotope is carbon-12, right? So we have, in this case, carbon-12. Well, no, this is the box. This is carbon-14. Know the difference what you're looking at. This is the box, talks about all the isotopes in the element. This is talking about one particular atom. This is talking about one particular atom. Because when you're talking about the number of particles, that's a whole number. When you have different isotopes, they're going to have different numbers of neutrons in each of the isotopes. Okay. We'll keep rolling. Rolling, rolling, rolling. This shouldn't look foreign to you. You actually did the handout, the FETSIM handout worksheet, and the last question on the review questions was actually a huge table, and you were given isotope notation was one of the columns here. You had another column for charge. If you work the worksheet to completion, then you've actually done something a lot harder than this. So this should be easier for you on the quiz. Now let's see how we attack this. You're going to be told what the element is. So if you know the element name, what else do you know? The atomic number, right. So you look up the symbol on the atomic table, on the periodic table, and I'm looking for silicon. Silicon is number 14. Do I automatically know what the mass number is?
Yeah.
I do?
Yes, you do. It's 28. Because you had the 14 because you have the number of neutrons and the number of protons.
So, do I know what the number of protons is? How do I know that it's 14?
Because the atomic number.
The atomic number is the number of protons. Oh, well, look at this. 14, 14, 14. 14, 14, 14, right? Oh, wait a minute. Was it supposed to work out like that?
No.
Okay. It could. It might not. You just don't know. You take the information you got and you use it to find the information that you need. With the mass number is the sum of the particles that actually have mass, which are the neutrons and protons, and so I can put a 28 right here. Now, remember what I told you several minutes ago, unless told otherwise, assume it's a neutral, so the number of negatively charged particles must equal the number of positively charged particles. And so look, we got 14, 14, 14, 14, 14, 14, across the board, except for the mass number. Okay, so let's tackle another one. Is there somebody potassium in here? Whose element is potassium? That's yours? Okay, what's your atomic number?
The atomic number was, hang on, I have
Oh, you should know this. This is your element. It's 1 through 20.
It's 19.
It's 19. It's either 1 through 20 or 19. Okay, so if you know that the atomic number is 19, then you know what else is 19? Number of protons. Okay? If you know the number of protons, you know the number of electrons. 19, 19, 19. All right, at this point,
39 minus.
you efficient students will start working vertically on this table. Oh, you say, okay, every time I have protons, I got electrons. Every time I have atomic number, I have the same atomic number. So you efficient working students will start working vertically on these tables. We have one more box to fill. How many neutrons are there if the mass number is 39 and there are 19 protons? I'm smelling a 20 right there.
What? This is so confusing.
No. Okay, so
Why 20 though?
if you are confused, you refer back to those equations where the mass number is equal to number of protons, number of electrons. You're trying to find out how many neutrons, so you would solve this equation for a number of neutrons. Substitute variables. Mass number 39 minus number of protons 19. 39 minus 19 is equal to 20. Okay. Some people just do this in their head. Some people need to write it out a few times, which is okay, right? But you know what? I'm going to require that you remember these relationships.
That's me, Master. Oh my gosh, you should.
I'm not going to give you the equations on the quiz. So here are some things that I do to try to help. The atomic number, number of protons, the dash number is the mass number. The mass number is the sum of the particles that actually have mass. And in a neutral atoms, the number of electrons equals the number of protons. If you can just remember those basic facts, knocking out a table like this is easy peasy, lemon squeezy. So I'm sure you can do it. I'm going to give you a sheet, and you'll have a little bit more practice before the quiz. Good. Good.
Wait, one plus one.
Today.